Hello everyone, this is quarter from 19th. Today's day 99 in my challenge day. And what I'm going to learn is about the Fresnel equation and the Schlick approximation in the ray tracing, I think. Actually, I've ever already learned about this concept in my previous computer graphics course, but I forgot about it. So I forgot about what was about the Cook-Torrance-BRDF equation and also the terms in the Cook-Torrance-BRDF. So I need to recap for it. And I see there is an assignment in the this rendering course. So in the next few videos, I'm going to just watch these courses, and at the assignment chapter, I'm going to implement it using the Vulkan API. So that's my short plan. Long for short, let's start. For whom curious about what is this course from, this is course from the 2 minutes paper, the famous YouTuber who reviewed the papers in the 2 minutes, actually not the 2 minutes. You can always check his YouTube channel and see this series if you're interested in. Okay, let's start.
Image from physical reality, we have an interface that is air and glass. What I see here is that there is reflection and there is refraction. So in case not everyone understands the term. Reflection is Lichtreflexion, and refraction is Brechung, right? With my horribly broken German. But thank God this course is not in German, everyone would cry. But you guys and girls have it easy, because in Hungarian you would say fény visszaverődés and fénytörés. So I think reflection and refraction is much better than that. At least much more convenient. Question, which is stronger? Which effect is stronger?
Reflection.
Raise your hand if you think that refraction, that this is this effect is stronger.
Here is the question about this example or in general?
In this example, yes. So I can see that the refraction has a more pronounced effect than reflection here. Okay, because we will deal with this in a second. And what we can do is we can actually write up the vectors that we have been talking about for a case like that. This is towards the direction of the light source. There is a surface normal. It looks like this, so the normal looks upward. This is where it's reflected, this is where it's transmitted. We don't have a vector for that, and we have the different angles for this. Wonderful. So let's take a look at the simplified version of Fresnel's equation. simplified version of Fresnel's equation. This one at least is called Schlick's approximation. We have no idea what this is about. This is a not so complicated thing. What this gives me is the probability of reflection. So R of theta is the probability of reflection. So as I have seen the image, I am interested in what is the probability of reflection and refraction. Because I imagine that the probability of refraction is higher in this case, and I would like to compute it in some way in my computer program. Well, let's take a quick look at this. R of theta is the probability of reflection. And this is important to remember because during our calculations I will forget this approximately 15 times. So may I ask your name?
Lisa.
Lisa, okay. Well, if I ask you what is R theta, you will tell me that this is the probability of reflection.
Probability of reflection.
Yes, and exactly, because I... Seriously, I will be forgetting it all the time. R0 is the probability of reflection on normal incidence. So this means that light is coming from, if it would be coming from above, what are the chances that it gets reflected? And R0 can be given by this expression. We'll be talking about this. N1 and N2 are basically indices of refraction. We will have examples with that too. But let's quickly go through this and see if physics makes any sense. Well, for an air vacuum medium, we have, let's say, the index of refraction of air is 1. And this N1 is the medium that we go into. So for instance here, glass. And let's see what happens there. But before we do that, T is the probability of transmission. Obviously, if the light is not, we forget absorption for now. If light is not reflected, then there is refraction. It's simple as that. So if I add up these two probabilities, I get 1. So let's play with it. R at 0 degrees is R0. Why? Because cosine of theta, so the cosine of 0 degrees is 1. So on the right side I have 1 minus 1, so the second term is killed by this 0. Therefore I will have R0. And R at 0 degrees, this is the theta is the degrees, the angle of the incoming light, 0 degrees, so it means that it comes from upwards. What is it? This is the probability of reflection of normal incidence. So this is basically the very same thing. So if it comes like this, what is the probability of it coming back, bouncing off of the glass? What's up with 90 degrees? Well, 90 degrees, the sine of theta is 0, therefore I will have both of these terms. Very simple. And this is going to be 1. So the probability of reflection at 90 degrees is 1. Because imagine that I'm coming from above, then this means that there is a very likely chance that I'm going to get through. So imagine a super crowded bus in the morning, and you just cannot fit in there. How would you like to go in if you don't care about the health and the intactness of the other people? Well, you will just run in there and, hopefully they will make some space. I have the best probability if I run towards them. If I would be running from the side, it would be very likely that they would just push me back. There's a high chance that I would be reflected. So I want refraction. I want to get on the bus. Okay, so as I raise this angle from normal incidence, the more probability there is for the ray to bounce back. So this, for now, seems to make some sense. Yes?
But is it still reflection at 90 degrees and not just the light source itself?
You have to think in terms of limits. So what is the probability at 89 degrees? It's going to get reflected. If you just raise that, you are going to approach the probability of 1. So this is a bit boggling the mind, but you can see that there's like a continuous transition. From here, there's high probability for refraction. As I go towards 90 degrees, there's more probability for reflection. And we define that at 90 degrees, we say that it is reflection because I am moving along the boundary, I'm not entering the glass. By the way, that's a great question. I was thinking about this too. From here, there's high probability for refraction. As I go towards 90 degrees, there's more probability for reflection. And we define that at 90 degrees, we say that it is reflection because I am moving along the boundary, I'm not entering the glass. By the way, that's a great question. I was thinking about this too before. So let's say that the index of refraction of glass is 1.5. Let's compute this thing quickly. It's 0.5 over 2.5 squared, and I do the very same substitution for the rest of the equation. But before I get this, what do I expect from the plot? That's another important mathematical principle. Do this all the time. Before you compute the result, state what you would expect from the result, because this gives you a much higher level of understanding. Well, I'm interested in R of theta. What does R of theta mean?
Probability of reflection.
Excellent. Okay, Lisa nails it again. So the probability of reflection at 0 degrees, I would say, is something very low, right? Okay, so I have written this here, that R of 0 is less than 0.1 because it's
When the light.
It's the probability of, I mean, R0 is the probability of.
Oh, sorry, of reflection.
Yes, so the probability of reflection is low. I would say less than 10%. Okay, so if I come from up, so the probability of reflection is low. I would say less than 10%. Okay, so if I come from upwards, refraction is likely. I'm very likely to get on the bus if I ram into the people from the front. Okay, what's up with, for instance, 60 degrees? Well, we know exactly what happens at 60 degrees because how many degrees do we have here? What is the incidence now? It's 60. And we can see that at 60 degrees there is a chance for refraction and reflection. And the refraction chance is? Higher, exactly. So what I would imagine is that at 60 degrees there is a higher chance of reflection. There is than the previous one, I mean, but refraction is still stronger. As you can see on the image, we are going to compute this, and we are going to let nature be our judge whether the calculation is correct or not. So 60 degrees, I quickly convert it to radians. That's more or less 1. And so R of 1 is 0.2. This means 20% chance of reflection, 80% of refraction. This seems to be in line of what I see here, but this is just my expectation. And what we have been talking about, pi over 2, this means 90-degree angle. I would expect it to be 1. So if I convert it to radians, then this is 1.7. So R of 1.7, I expect it to be 1. Let's put all of these together and let's do what engineers do all the time. Open Wolfram Alpha and try to plot this. So I imagine that R of 0 is less than 0.1. So getting on the bus easily. Well, R at 0 is less than 0.1. So far so good. R at 1 is less than 0.2. This is the 60 degrees, mostly refraction. Well, R at 1 is less than 0.2, so check mark. And R at around 1.7 is indeed around 1. So apparently, physicists are small people, and physics makes sense. So pretty good. But there is something fishy about this. So this is correct. I mean, what we see here is in line with our expectations. But there's something fishy about this plot. Raise your hand if you know what it is. Okay, I'll give you a hint. This plots R of theta, which is?
Probability of reflection.
This is the probability of reflection. Okay. What happens after, I don't know, if I would just extrapolate, what would happen at not 1.5 but 2? What would I measure? I think it would be something like the very least.
Minus?
It's going upwards. But it would be at least 3. I don't know about you, but I don't know about probabilities that can be larger than 1. Right? So this would give me some fishy results if I would substitute something like that. So let's try to shed some more light on it. What if I have a vacuum-vacuum interaction? So below, I don't have glass anymore, I have vacuum. Well, the index of refraction of vacuum is 1. So let's just substitute 1 here. So this is going to be 0, and I'm going to have the second term, 1 minus cosine of theta to the 5th. Why? Because this is 0, and this is 1 minus 0, so I will keep this term. Okay, engineering mode. What do we expect from this plot? I have vacuum, or air, if you wish, if you will, and vacuum again. I start a ray of light. What will happen with probability of 1? Reflection or refraction? Raise your hand if you know.
Should be no reflection.
There should be no reflection. Exactly. Why?
Because there is no interaction of the medium.
Exactly. So the definition of vacuum is, again, nothing. There's nothing in there. There's nothing that could reflect this light, this ray of light back. If there's vacuum, we expect rays of light to travel in vacuum indefinitely. There's no way that it could be reflected. So, since R0 is the probability of
Reflection.
then this R theta. What do I think this should be? If there is only refraction, then this R of theta will be
0.
fantastic. Okay. Well, let's plot this. This looks like 1 minus cosine theta to the 5th. This is already fishy, but let's take a look. Blah, blah, blah. This is what I've been talking about. So I expect it to be 0. Let's plot it. And this looks like this, which is not constant 0 by any stretch. So the question is, what went terribly wrong here? And let's plot it. And this looks like this, which is not constant 0 by any stretch. So the question is, what went terribly wrong here? And it's very easy. The Schlick approximation is an approximation. It's good for interfaces which are vacuum or air and something, and not something. Something something. Okay, so A and B. It works well, but it's a quick approximation because this is the original Fresnel equation, and this is much more expensive to compute, and this other one was much quicker, but it's a bit limited in use. So let's give it a crack. So what would this say about a vacuum-vacuum interaction? Well, I would substitute N1 and N2 equals 1. This is the index of refraction of vacuum. I get the very same thing back, just the N1s and N2s are gone. I'm going to use a trigonometric identity which says that the square root of 1 minus the sine of square something is a cosine. Okay, so let's substitute these for the cosines. Got it? So what I see here is the cosine of theta minus cosine theta. So what is this expression exactly? How much is it? It's 0, exactly. And this is what I was expecting. So apparently physicists, again, are smart people. There is still one thing that we don't know, and it's about angles. So we know about probabilities. Whatever you give me, I can tell you what is the probability that light gets reflected or refracted. I know the probabilities, but I don't know about angles. And what we need to know.
Okay, so I will do the Snell's law in the next video. So today I learned about the Fresnel equation. Uh, in the simplified version is Schlick's approximation. So the equation for this array can be refracted to the surface or reflected on the surface. So depending on the material properties on the surface, the ray may be just refracted, whole the ray just refracted to the surface, or just the whole amount reflected on the surface, or maybe a ray, a single ray, is separated into two parts, which is the refract ray or the reflected ray. So the amount of effect each part is dependent on the medium and the material property either. In the case of glass and glass to air medium interaction, the reflected amount is stronger than reflected amount in regard to the incidence angle is 60 degrees. So we can write the vector notation on this image. So n is the surface normal vector, and the L is the incident light direction, and R is outgoing light direction, and theta I is the angle between the incident light and the surface normal, and the theta R is an angle between the surface normal and the outgoing direction. And minus n is just a reversal of the direction of the surface normal. No, reversal of the surface normal, and the theta t is the angle between the reversed surface normal and the refracted ray. The Snell's law is related to calculate the theta t in terms of the two medium difference between the upper side medium and the downside medium. And what we want to know to get, what we want to get from this Fresnel equation is the probability of the reflection on the surface. Uh, because we only have two types of interactions, which is the case of the reflection and the refraction, by the axioms of the probability, if the probability of the reflection is equal to the r theta, the transmittance amount, the probability of the refraction will be 1 minus r theta, and we denote that is as t theta, the abbreviation of the transmission. And Schlick's approximation give us the probability of reflection r theta, as I mentioned already. And we can write this term, write this equation. R0 is the probability of the reflection on normal incidence. So we put the R0 to the theta. The left side term will be the R0, and there is still R0, and plus 1 minus R0 multiplied by the 1 minus cos theta, but at the degree of 0, the cosine theta is equal to 1. So this term will become 0. So we can remove this term. So the equation is established, and we can express r theta as the with the index of refraction of the new medium. I didn't understand. I didn't fully understand about it. So there's more contents in the my notes, but my companion comes to in the laboratory, so I need to stop recording just right now. So that's all for today's recording. Thanks for watching. See you next video.